Let us talk about this problem. We are given an array of integers. This array represents prices of a stock on n consecutive days. Our task is to find out span of stock on every day. Now what is span? Span on a day is number of consecutive days including the current day and days just before it which have value equal or smaller. That's the span for a day. Let's understand it with these examples. We are given prices of a stock for 10 days here, right? We have 10 items, 5 and 5, 10 items. First day it's 13, then 15, then 12, then 14, then 16, then 8 and so on. We need to find out span of a stock on every day. On day 1, span is always 1 because there is nothing on the left of it and only this day is included in the span. Let's now see for day 2. How did we define span? We defined span this way. It's number of consecutive days on the left side including the current day which have values smaller or equal. So both 13 and 15 including the current day we have values smaller or same. That's why the count is 2. Let's now see 12. Number of consecutive days on the left side and the current day itself which have values smaller or same. So if you go on the left of 12 you find 15 and 15 itself is greater. So you have only one item in the span which is 12. Let's now see 14. For 14 you have 14, then you have 12 and 15 is greater. So we stop here because we are saying consecutive. We can't include 13 because it's not consecutive. So that's why our output is 2. Number of consecutive days which have value smaller or equal. So one thing is current item is always included, right? Because we include the current item. So span on a day is at least once and it depends how many elements, consecutive elements on the left side have values smaller or equal and according to that it goes beyond 1. Let's now see 16. For 16 everything on the left side is smaller or equal including 16. So we have 5 days. 1, 2, 3, 4, 5. Let's now see 8. So the element which is just on the left of 8 is greater. So we can't beyond it. We can't go beyond it because we are talking about consecutive days. So for 8 count is 1. For 6 the case is same. The element just on left of it is greater. So span is 1. For 4 again span is 1. For 10 we have 4 days on 10 left side which have value smaller or same, right, including 10. On 30 everything on the left side is smaller. There are total 10 elements including 30. So span for 30 is 10. Here are some corner cases. If our array is sorted in increasing order then span is also going to be in increasing order. For day 1 it's 1. For day 1 it's always 1 whatever your input is. For day 2 it's 2 because 2 elements consecutive are smaller. For day 3 it's 3 because all 3 are smaller or equal to 30. For day 4 it's 4. If your array is sorted in reverse order or decreasing order then the span for every day is 1 because the element on just left of it is greater and you can't have span more than 1. So 30 left side is greater, 20 left side is greater, 10 left side is greater. So you have span of every day is 1. Let us now quickly check if you understood the problem really well or not. Please pause this video and try to guess the output for this input. As we have said, span for day 1 is always 1, so it's going to be 1. For this item, the element just on left of it is greater, so this is also going to be 1. For 25, the element on left side is smaller, so it's going to be 1 plus 1, 2, right, these two items. So output is 2. For 28, there are 3 consecutive elements which are smaller or equal on left of 28 including 28. So our output is 3. For 27, the element which is just on left side of 27 is greater. So it's going to be 1. Only 27 is going to be part of span. 29, how many elements on left are smaller or equal including 29? We have 5 elements. 1, 2, 3, 4, 5. So our output is 5. Now I guess you must have understood the problem really well. Please pause this video and try to write down a function that takes an array as an argument and prints a span for this array. Let us first talk about naive solution to solve the problem. And the idea of naive solution is very simple. For every element, we go on the left side of it and we keep on moving to the left side while we see smaller or equal to elements. As soon as we see an element which is greater, we stop. And with the help of count of iterations, we can find out the span of this element. For example, 14. We know the span of 14 is 3 because 12, 13, 14, these three elements come under the span. So to find out the span, we initialize the span as 1 because we know 14 itself or any element itself is part of the span. Now we go to the left side and we see this 13 is smaller, we increment the span. Now we go to the left side again, 12 is smaller, we increment the span. Now we come to 18, we see a greater element, so we stop the loop, right? And when we stop the loop, our span would become 3. So that's what we do for every element. So we are simply going to run a loop for every element from 0 to n minus 1. And for every element, we are going to go on the left side of it. So we are initializing the span as 1 because every element itself is part of the span. Then we are going to the left side beginning with I minus 1 and we go till j is greater than 0, greater than equal to 0, right? We can't go beyond the first element. And this condition should also be true. We should be seeing a smaller or equal to elements. We need to stop as soon as we find a greater element, right? So we run this loop while these two conditions are true. Both of them are true. And inside this loop, we are simply incrementing the span. When we come out of this loop, we'll have the span of this element. So we begin from here. There's nothing on the left of it, right? J would be initially minus 1. This condition would not be true. So we'll have the span for this as 1. When we come here, we'll go in, we'll check for j equal to I minus 1. Then this condition is true, but this condition is false, right? This element is greater. So we'll break the loop and we'll have span as 1. For 13, we'll go inside the loop once, right? Because both these conditions will be true for 12. So we'll have the span as 2. For 14, we'll do 2 iterations of this loop and we'll have span as 3. For 11, we'll not run inside the loop. Our span is going to remain 1. For 16, we are going to run this loop 4 times. So our span is going to become 5. So this is how the solution is going to run. Now what is the time complexity? If you try to find an upper bound on the time complexity of the solution, you can find the upper bound as big O of n square. And when do we get n square iterations? We get the worst case time complexity when our array is sorted in increasing order. For example, if our array is 10, 20, 30, 40, 100, then we are going to take exactly n square time because for every element you are going to do I iterations. If the index of this element is I, 0, 1, 2, 3. 3 is the index of this element and we are going to do 3 iterations, right? So worst case is going to happen when you have a sorted array. Now please pause this video and try to think of a solution that works in linear time. Before we talk about efficient solution, let's first talk about few observations. The first observation is a span of current element is equal to index of current element minus index of closest greater element on left side. We are going to call it previous greater element as well. So if you see 60, there is nothing on the left side, so we always know span of this is 1. Now if you see 10, its index is 1 and closest greater element on left side is 60 whose index is 0. So this is 1 minus 0, span of this item. 20, index of closest greater element on left side. So there is only one greater element and this is the closest greater element. So index of this is 2 and this index is 0. So we have span as 2 minus 0. 40, index of closest greater element on left side is 0 and its index is 3. So it's 3 minus 0. For this element, index of closest greater element on left side is 40 because 40 is the closest greater element for 35. So span of this is 4 minus 3, 1. For this element, closest greater element on left side is 35. Please note that there are 3 greater elements for 30, 35, 40 and 60. Out of these 3, the closest one is 35, closest one on the left side. So we have span as 5 minus 4. Span for this closest greater element on left side, there is only one greater element. So span for this is 6 minus 0, 6. 70. There is no greater element on left side. So for that case, our span is index plus 1 because everything is part of the span. So 7 plus 1. So we can say if there is a greater element on left side. Otherwise, we have index plus 1, index of current element plus 1. So for this case, we have span as 7 plus 1. For 65, we have an element 70 which is greater than this, and its index is 7. The closest greater is 70, although there is only one greater, and that's the closest one, 70. So span for this is 8 minus 7, which is 1. You can verify that these spans are correct, and we got 1 for this using this rule because there is no greater element. So we can say index of current element plus 1, 0 plus 1. So this is how we can get the span of every item. Now please pause this video and try to think of a way to find index of closest greater element on the left side. Let us now talk about second observation for the efficient solution. So in this efficient solution, we are going to traverse the elements from left to right. Say if our array elements are x0, x1, x2, xi, xi plus 1, x and xn minus 1. We are going to traverse the array from left to right. It's a linear time solution. And for every element, we are going to find its span, and then we are going to go to the next element. Now the question arises, when you have traversed till xi, you must be having a span of all the items from x0 to xi. And now from xi, if you go to xi plus 1, you traverse the next element. What all information you need about these elements so that you don't miss any previous greater element, and you can quickly find previous greater element. Let's understand this with this example. Let's say we have traversed this array from left to right, and say we have traversed till 35. Now, when we have traversed till 35, we do not know what all is going to come here. There might be 38 here, or 10 here, or any number, or 100 here, right? Next number can be anything. And there can be any number of remaining numbers. We don't know. So if we process till 35, what all information we should store so that we can find the span of upcoming items. Suppose we have found the span of all the items from 60 to 35. Now what all information we should store somewhere so that we can find a span of all the remaining items. Now if there is an item coming after 35, there are multiple possibilities. The first possibility is this item is smaller than 35. In that case, the previous greater element for the upcoming item is simply 35. So we need 35, right? Now suppose the element is greater than 35. Now if the element is between 35 and 40, then previous greater element for that element is going to be 40. And if the element is between 40 and 60, then the previous greater element for that element is going to be 60. And if the upcoming element after 35 is greater than 60, then we know span of that element is, because there is no previous greater element, span of that element is index of that element plus 1. So we need to store these three items, 35, 40 and 60, right? 35, its previous greater, and then its previous greater. This is the chain that we need to store for upcoming elements. And in which order we are going to process these elements? First, we are going to compare the upcoming element with 35. And if 35 is greater, then we decide, okay, 35 is the span of this element. And if 35 is smaller, then does 35 still remain useful for us? For example, let's say we have an element 38 here. Now, say 38 is greater than 35. Now 35 become useless for us, because next greater element, say we are to process till this point, for 38 next greater element is 40, and 40's next greater element is 60. So the elements which are useful for us are 60, 40 and 38. And in which order we are going to process these three elements? Whatever comes next, we are going to compare it with 38 first. If it is smaller than 38, then we decide that, okay, previous greater for upcoming element is 38. And if it is between 38 and 40, then we are going to decide, okay, previous greater for that element is 40. And if it is between 40 and 60, then we say, okay, previous greater for that element is 60, right? And if the upcoming element is greater than 60 itself, then we are going to say, okay, the span for this element is, because there is no previous greater element, span for this element is its index plus 1. So this is the idea. We need to store element that we just processed. We need to store previous greater of this element, and then we need to store previous greater of that element. This is the sequence we need to store. And how do we store these elements? We need to store them in such a way that this element should be processed at the end, then this element should be processed, and then this element should be processed. 60 should be looked at the end, right? Because say next element is 37, then if it's smaller than 38, then we don't need to look for 60. And if it's between 38 and 40, then we need to remove this element. It's of no use for us, and we need to compare the upcoming element with 40. And if the upcoming element is greater than 40, then this also becomes useless, and we need to compare with 60. So this is the order in which we need to process the chain. This is our just processed element. Its next greater is 40, its next greater is 60. Sorry, its previous greater is 40 and its previous greater is 60. This is the order in which we need to process. And what is this order? This order is last in, first out order. 38 was processed last, right? And we need to compare the upcoming element first with 38. 40 was processed next to last, right? Second last. So, and we need to compare our upcoming element with 40 next, then 60, and if there are more, then more elements. So this is a LIFO order, and for this reason we store these previous greater elements in a stack. Say we have this array x0 to xn minus 1, and we have processed till xi. So our stack is going to contain xi at the top, xi's previous greater element, closest element on the left side which is greater than xi. This element is going to be just below it in the stack, and the element which is just below xi previous is xi previous greater element for xi previous. This is how we need to maintain the stack. Now please pause this video and try to write down a complete stack based implementation for this problem. Here is implementation of the efficient approach. Here I have written pseudocode. The code is close to both C++ and Java. So in this pseudocode, we are first creating a stack, and then we are processing the first item. You can create a stack using C++ syntax here, or you can create a stack using Java syntax. I have written simply stack as. It means we are creating a stack here. After creating the stack, we are processing the first element. So when we say processing the first element, we mean that we are pushing it into the stack and we are deciding its span. We always know that span of first element is always 1. So we are simply printing the span of first element as 1. Again, I have used some pseudocode for printing this on the screen. You can replace this print with cout, or you can replace this print with system.out.println. So I am printing the span of first item. And if you take a closer look, you can notice that instead of pushing the element, I am pushing its index. I am pushing the index of first item. And here I am pushing the index of other items. So I'm always pushing indexes into the stack. What is the reason for processing these indexes? The reason is simple. When we talked about stock span in terms of previous greater element, we need index of previous greater element to know the span of current item. What is the span of current item? It is index of current item minus index of previous greater element, if there is a previous greater element. If there is no previous greater element, if this element is the greatest so far, then span of this item is current item's index plus 1. Otherwise, it is index of previous greater. So whatever is there in the stack is your previous greater, and we need index of it. And if we have the index, we can get the value as well for comparison. After processing the first element, we process the remaining elements. We begin with second element, index equal to 1. And for every element that we process, we have one more loop inside it. And inside this loop, what are we doing? we are removing all the items from top of the stack which are smaller or equal to the current item. So we are using s.top as an index because stack is going to store all the indexes only, and we are checking the item at this index with the current item, array i's current item. If it is smaller or equal, we are removing the top item from the stack. So we first remove all the smaller or equal to items. When we come here, either the stack is empty or our current item is smaller than top of the stack. If a stack is empty, then the current item is the largest item seen so far. In that case, its span is I plus 1. And if the stack is not empty, then whatever is at the top of the stack is previous greater of current item. In that case, we take the index of current item, we subtract the stack top, which is previous greater, and that's how we find the span of current item, right? So we have two cases here. If stack is empty, then span is I plus 1. If stack is not empty, then span is I minus stack top, which is previous greater of I. After finding the span, we print the span, and after we have printed the span of current item, we push the current item so that it is used for further processing. Let us now see execution of this code step by step for this array example. The array is 60, 10, 20, 15, 35 and 50, and these are the indexes of the elements in this array. So what we do here, we first create an empty stack, then we push 0, index of the first item, then we print the span of first item as 1. So before loop we have this condition. We have 0 in the stack, we have printed 1 on the screen. Now we begin with the second item 10, and for every item we are going to first remove all the smaller or equal elements from top of the stack. Currently top of the stack is 60, so we are not going to remove anything, we are simply going to push 10 into the stack. So when we say push 10, we mean index of 10. Index of 10 is 1, so 1 is pushed, and then we print the span of this. And how do we figure out the span? See, we did not enter inside the loop for 10 because there was nothing on the top which was smaller or equal. So we come out of the loop and we find the span this way. We find the index of current element, which is I is 1 here, and top of the stack is 0. So 1 minus 0 is span of 1. So span of 1 is 1. We print this on the output. Now we begin the next iteration. Before beginning the next iteration, we push this item into the stack, right? So you can notice we have pushed 1 into the stack, right? So our stack is now 0, 1 and item 1 is printed. Now we begin the next iteration. I equal to 2, we come to 20 and we again do this thing, we check top of the stack is small or equal. So top of the stack is 10, which is smaller. So we are going to remove 10 now. So this 1 is going to go away from the stack. And once this 1 is gone, we are going to come here because now top is 60, which is greater. We'll come out of the loop. And here we are going to find out the span of this item. Span of this item is going to be I minus stack top. I is 2, stack top is 0, so our span is 2. And now we are going to push this 2 into the stack here, right? And before pushing, we are printing the span on the screen. So we now see 2 on the screen, and now our stack has 0 and 2. Now we are going to begin the next iteration. For I equal to 3 and the element at index 3 is 15. We compare 15 with the top of the stack, and top of the stack is greater. So we do not enter inside this loop. Now we come here, and when we come here, we decide the span of current item. The span of this item is going to be 3 minus 2, which is 1. So we print the span on the screen, and we also push this index 3 into the stack. So now our stack has 0, 2, 3. Now we process the next item, I equal to 4. So when you see 35, you can notice that this element 15, which is top of the stack, it's smaller, so you're going to pop it. Then next item 20, you are also going to pop it. So you are going to run this loop 2 times, right? You are going to pop 2 items. And then top of the stack is 60, which is greater, so you are going to come out of this loop after running 2 times. Then you are going to find out the span of 35. Span of 35 is 4 minus 0, right? Top of the stack is now 0, so 4 minus 0 here is your span 4. So you'll print 4 on the screen. And after printing 4, you will push 4 into the stack. Then you will come to the next item 50. When you come to 50, you will see that top of the stack is smaller, so you will take out the top, right? You will run this loop once, and then you will find the span of the current item as I minus top. So I is 5 and top is 0. So we are going to get the span as 5 minus 0, 5. And then we are going to push 5 to the stack. So after the last iteration, our stack is like this, and we have printed the span of last item. Let us analyze this solution. When we first see this solution, it looks like a quadratic time solution, but it is actually a linear time solution. How do we get linear time? Let's take a closer look at the solution. If we take a closer look, we can notice that every item is pushed into the stack exactly once, and every item is popped out of the stack at most once. Let's see how is it true. So if you see the first item, it's pushed here, and remaining n minus 1 items are pushed here. And when do we pop items? Inside this loop. So we are going to pop whatever has been pushed, right? So we are going to pop at most 10 items. So we are doing at most 2n stack operations, n push operations, and at most n pop operations. Every push operation or pop operation on a stack takes constant time. So our overall time complexity is theta n. Now how much auxiliary space the solution requires? The auxiliary space varies from input to input. If your array is sorted in decreasing order, for example 30, 20, 10, 5, then everything is going into the stack, right? Because you push into the stack if top of the stack is greater. So when you come out of the loop, you will have everything in the stack. But if your stack array is sorted in increasing order like 5, 10, 20, 30, in this case you will have at most one item in the stack at every movement. You will push 5, when you come to 10 you will pop 5 and push 10. Here you will pop 10 and push 20. Pop 20 and push 30. So it depends. It's going to take big O of one auxiliary space in this case. Your stack will have at most one item. But in the earlier case, it's going to take theta n space. So we can say auxiliary space requirement of the solution is big O of n.